Swayam Prabha. Digital India. Educated India.
Last class we have discussed semiconducting current, mostly diffusion current and drift current. From there we move to PN junction. We have discussed different condition of PN junction. We said equilibrium condition, and then forward bias and reverse bias, and we look about different current components within PN junction diode. We calculated built-in potential VBI, that is KT by Q ln NAND by NI square. And ultimately we reach to the diode PN junction diode current. This is the IV characteristics of the diode. Okay. This is the forward portion or forward bias of the diode, which we have discussed in the last class. In forward bias, the diode current is IS exponential Vd over Vt. Vd is the voltage across diode, and Vt is the thermal voltage, whose value is around 26 millivolt, okay, at room temperature, right? And the expression is KT over Q, so that is our Vt, okay. KT over Q or KT over E is the Vt. This IS exponential Vd over Vt, that is the current of the PN junction diode in the forward bias. So as you increase the voltage across diode, the current in the diode will increase exponentially. Here IS is the reverse saturation current, okay, reverse saturation current. If you see the reverse bias portion, the current is basically IS, that is the reverse saturation current, and it is of the order of pico to femtoamp, depending on the dimension of the diode, okay. And of course it also depends on the temperature of operation and all that. But the point to be noted here, the diode current is independent of diode voltage, okay. So if you see carefully, diode is allowing current in the forward bias, and in the reverse bias there is almost no current. So we can consider diode as a switch, okay, where when diode is in the off state, reverse bias, so then the switch is in the off state, okay, and when diode is in the forward bias, then diode is acting as on state. So so if diode is in the off state, so diode will, so then entire voltage will be across the diode, okay. Say I have a resistor here and a voltage source, and I have a diode. If the diode is in the off state, then there will be no current in the circuit, so entire voltage will be across the diode. On the other hand, if the diode is on, okay, then diode will act as a closed circuit, sorry. So then diode will act as a closed circuit, okay, or switch is on. So there will be hardly any voltage drop across diode. In practice, we call this voltage drop when the diode is on as V gamma, okay, that is the cut-in voltage, or also known as threshold voltage. If the voltage is more than the V gamma, then the diode will be on, and if it is less than V gamma, there is hardly any voltage. So that is, so this is your basically your V gamma, okay. In case of germanium, it is around 0.2 volt, and in case of silicon, it's around 0.6 to 0.7 volt, right? Now, if we keep on increasing the increasing this reverse bias, okay, at some point, all of a sudden, you will find current in the diode increases rapidly, okay, even there is any change in the diode voltage, across the diode voltage, okay. So this particular phenomena is known as breakdown, where there will be hardly any change in the diode voltage beyond a point known as breakdown voltage, which is designated as VBD here, okay. So beyond this point, the diode current will increase drastically, but there will be hardly any change in the voltage across this diode, okay. And this breakdown, there can be two mechanisms through which this breakdown occurs. One is known as avalanche breakdown, and the other one is known as Jenner breakdown, okay. Now, in case of avalanche breakdown, okay, so both these phenomena occurs in the reverse bias. So that means I have my PN junction, in reverse bias means supply positive side of the supply voltage is connected to N, and negative supply is connected to P. And you see, when it is in the reverse bias, the depletion region increases, right? That we have discussed in the last class. So the immobile carrier in the N side, that is this positive immobile ion, that is phosphorus, and there is negative immobile ions, that is boron in the P side. Now what happens, there will be electric field here, okay, at this junction, and electric field is from positive to negative side. Now, as this supply voltage, reverse bias voltage increases, okay, initially the diode current is almost independent of this reverse bias voltage, okay. Now if you keep on increasing this voltage in the reverse bias, as I said, at some point it will reach to the breakdown voltage, and the breakdown will occur. In case of avalanche breakdown, what happens is the minority carriers, okay, the minority carriers in case of P side, minority carriers are electrons, okay. So these electrons, when they are accelerated because of this electric field, okay, it might happen that the electric field is so large that these electrons, these minority carrier from the P side, will will achieve a lot of energy, and they will reach a critical value, their energy, and they manage to break covalent bonds. Okay, so then from one electron, if they manage to break covalent bonds, they will create electron hole pair, and then those electrons will then again will be energized, and then they will cause then they will break other covalent bonds and create additional electron hole pairs, and this process will go on, and all of a sudden you will have lots of electrons and lots of holes in this depletion region, which was not there initially, because you understand that my minority carrier concentration is much less. So because of this less number of minority carrier, there is very little amount of current in the reverse bias. But as you keep on increasing the bias voltage, okay, the electric field will be higher and higher, and when this electric field will reach a critical value, the minority carriers, those are electrons on the right hand side and holes on the left hand side, that is in the N region, they will accelerate and they will collide with covalent bonds and manage to break the covalent bonds, will generate more and more the minority carriers, and all of a sudden we'll get lots of carriers, okay, which will cross the junction and can give rise to large amount of current. So that's basically your avalanche breakdown. Okay, in case of Zener breakdown, the phenomenon is little bit different. It occurs because of quantum mechanical tunneling. Okay, so in case of Zener, in case of Zener breakdown, we basically need highly doped P and N region. Okay, if your PN region is highly doped, the depletion region width will be much less. Okay, so if the depletion region width is less, then it is possible for the high energy carriers to tunnel the junction. Okay, so let me draw it once more. Here also we have reverse bias, the junction, because breakdown occurs in reverse bias, but in case of Zener breakdown, the doping concentration in both sides is quite high. That means the depletion region thickness will be much lower. Even if you increase the reverse voltage, okay, reverse bias, the depletion region will not it will not be very large. Okay, so it is possible for the carriers to tunnel through the junction. Okay, this will be more clearer if I draw the band gap. Okay, let's this is my P side. Okay, and this is my N side, right? So this is my N region and this is my P region, and I have used I have applied reverse bias. Okay, so the Fermi level will not be in the same line because I have applied bias. But what I want to show that the the electrons in the p side will be able to tunnel and reach the n side of the conduction band. Instead of crossing the barrier, they will basically tunnel this junction because the depletion width is not much and the electric field is quite high. So they managed to tunnel through this junction or through this depletion barrier, and from valence band of p side the electrons will reach the conduction band of n side, and this gives rise to quite a lot of current, and this happens when they are in the reverse bias. Okay, but this Zener breakdown, okay, requires high doping concentration. So usually the Zener breakdown occurs in lower voltage compared to that of avalanche breakdown. Okay, avalanche breakdown occurs in higher voltage compared to Zener. Now, so this is the symbol of the Zener diode. Okay, and we will discuss the application of Zener diode in the next chapter. But let me tell you, a very important application of Zener is it can be used as constant voltage reference. Okay, because you see here voltage is not changing. Okay, even if the current through the Zener is changing, so voltage remains the same even if there increase in current. So this Zener diode can act as a constant voltage reference circuit. Okay, now let's move and discuss diode model. Okay, so the reason we need to know diode model, because then it will be easier for us to design and analyze diode circuit. Okay, so we will start from very simple diode model to go more complex diode models. Okay, so this is the simplest diode model, which is known as ideal diode model. In this particular case, we, as you see in this plot of ID versus VD, okay, we are considering that there is no cut-in voltage, that is V gamma equal to 0. Okay, or sometime we represent VD on. They are both the same thing. They are 0 volt. Okay. We also assume that diode current increases when the voltage across diode is more than 0 volt. So diode current DC increases. Okay. In case of reverse bias, there is no current through the diode. Okay. So in forward bias, diode will act as a short circuit because there is no there is lot of current through the diode, and the voltage drop across the diode is 0. So diode will act as a short circuit in case of forward bias, and in case of reverse bias, diode will act as an open circuit because there is no current through the diode. So entire voltage will be across the diode. Okay, so this is the simplest diode model, which is known as ideal diode model. Okay, what about the second model I would like to discuss is constant voltage model. In the case of constant voltage model, diode will be on at VD on. Okay, VD on. So when the voltage is less than VD on, the current in the diode is 0 or the diode is off, and when the diode voltage is more than VD on or equal to VD on, there will be current in the diode. Okay, so in other words, when the diode voltage is less than VD on, it will act as open circuit. Okay, and when it is more than VD on, it will act as a we can replace this diode as a supply voltage of as a not supply voltage, as a voltage of VD on. Okay, you see the polarity of this voltage symbol. Okay, you see it is opposing the current flow. Okay, that is obvious because if the diode current is flowing in this direction, below this VD on there will be no current. So this VD on is basically opposing the current flow through the diode when the diode voltage is below VD on. So the polarity will be such that it will oppose the diode current. Okay, so this is basically the constant voltage model of the diode. The next model we would like to discuss is piecewise linear diode model. Okay, in this particular case, we are assuming that current through diode is 0 up to V gamma or VD on. Okay, however, when the voltage across the diode increases further, the current will increase linearly. Okay, current will increase linearly. So that means so you see current increases linearly. Okay, and we can associate this linear increase in current with a resistance. So we can, from the slope, we can find out resistance RF or 1 by RF. Okay, so that is the forward bias resistance of the PN junction diode. Okay, or forward resistance of the PN junction diode. We can have reverse resistance RR which will be very, very large. Okay, and in this particular, for this particular model of diode, we can consider this tends to infinity. So let me repeat it once more. Piecewise linear model. So as you see, as we move from ideal diode to constant voltage model to this piecewise linear model, we gradually moving towards the characteristic of the practical diode. Okay, so in piecewise linear model, below VD on or below V gamma, the diode current is 0. Okay, and above V gamma, the diode current increases linearly, although in reality it increases exponentially, but in this particular model we are assuming that diode current increases linearly, and from that slope we can find out the resistance or 1 by RF, that is the resistance associated with the forward bias of the diode. Okay, whereas in the reverse bias, the diode resistance can be considered very, very large because there is hardly any current through the diode, and we can usually represent as RR, which tends to infinity. Okay, now there are different types of application of the diode. We use diode as a light emitting diode. There is photodiode, there is solar cell, there is Schottky barrier diode, Zener diode, and so on and so forth. I thought I just mentioned different application. If you are interested, you can go through from books these different applications, or from the web the applications, different applications of the diode. Okay, PN junction diode. Now let's move to the second chapter of our course, that is diode circuits. Okay, so in the first chapter, what we have learned so far, we have learned the semiconducting material. We have talked about silicon, that is the group 4 element. We mentioned that we can dope silicon, and we should dope silicon because the intrinsic silicon gives very low current, and also the current depends on temperature because the intrinsic carrier concentration depends on temperature. So from there we discuss that we need to dope silicon, and we then discuss the p-type and n-type doping. If we dope with group 3 element, we get p-type doping, that is there the majority carrier concentrations are holes, and if we do doping with phosphorus or arsenic, then we will get n-type doping where the majority carriers are electrons. And from there we discuss current in semiconductors, that is diffusion current and drift current. Then we have talked about p-n junction diode. We discussed 3 specific conditions, that is equilibrium condition, forward bias condition, and reverse bias condition. And we have seen that the diode current is basically exponentially related to the voltage we have applied near the diode in the forward bias, while in the reverse bias the diode current doesn't depends on voltage. However, if you increase the diode voltage, after beyond a critical point, there will be breakdown will occur, and there is Jenner breakdown and avalanche breakdown. And at the end of the first chapter, we have discussed 3 different models of the diode. So we use those models to analyze, design and analyze diode circuits. So that is the whole purpose of discussing those models, because as you see, diode is a nonlinear device. The current and voltage relates exponentially, but we can simplify this exponential relation with ideal diode or constant voltage diode model or piecewise linear model to analyze different diode circuit. So as we have learned those models just now, we will use those diode models to analyze some diode circuits. So we'll go through some examples. Okay. Now, for example, in the first example, we are basically considering simple diode model or ideal diode model, where the diode is the voltage across diode is 0 when it is short, when it is on, and the voltage across diode is open circuit when the diode is off. Okay, so we are assuming here constant voltage model of the diode, and trying to analyze this try to analyze the circuit here. Okay, so this is the model we are assuming here, where when diode is on, voltage across diode will be 0. Okay, and when diode is off, then there will be no current through the diode. Okay, this is what we are assuming. And now so in this first example, we have a voltage source, a resistor R1, and a diode D1. Okay, now when this V in is less than 0 volt, okay, then diode is reverse bias, because you see we need to switch on the diode to take the diode more than 0 volt. Okay, so when V in is less than 0 volt, so diode is off. So if you see carefully, then the entire voltage will be So this entire voltage V in will be across this diode. Okay, because it is open circuit, so there is no current through this resistor. Okay, so this entire voltage V in will be across the diode. So we can say that V out equal to V in here. Okay, when diode is off, whereas when diode is on, so this is the diode is basically short circuited. So if you measure voltage here, you will get 0 volt because diode is short. So the entire V in will drop across this resistor R1. So if I plot transfer characteristics, that is V out over V in of this diode circuit here, okay, we will it is obvious that when diode is off, then entire voltage will be across the diode, that is V out equal to V in. Okay, when V in is less than 0, while when V in is more than 0, there is no current, there is no voltage drop across the diode. Okay, so this will be your transfer characteristic, that is when you are plotting V out versus V in. So below 0 volt, below 0 volt, the diode is off. So the output voltage is basically input voltage. So we will have a so the output will increase linearly with input. Okay, whereas when the input voltage is more than 0 volt, the diode is on, so entire voltage will be across R1. So if we measure voltage across diode, we will get 0 volt at the output. Okay, in the same fashion we can discuss example number 2, where we have two resistors R1 and R2, and we are measuring voltage or measuring output across R2 and diode D1 together. Okay, now in the same fashion we can discuss this example here also. When the V in is less than 0 volt, okay, diode is off, and when diode is off, there is no current through this circuit. There is no current because the diode is off. Okay, now so we can say this entire V in will be across this V out, because this is the highly resistive part of that, because this is open circuit. So we can say V out will be equal to V in. So that is this portion, slope equal to 1. Okay, so here you see V out equal to V in. Now if we forward bias the diode, so if we go V in more than, if we take V in more than 0 volt, so that will forward bias this diode D1, and so it will act as a short circuit. Okay, then this V in will drop between R1 and R2. So we will have this diode is short circuited. Okay, so V out will be the voltage drop across R2. Okay, and that voltage drop obviously will be equal to, V out will be equal to V1 V in over R1 plus R2 multiplied by R2. Okay, so that's basically my V out, and the slope is so that's basically my V out. So the slope is R2 over R1 plus R2. Okay, so here the slope was 1, and here the slope was R2 over R2 plus R1. Okay, so in the same fashion we can discuss other examples. For example, in example 3, I am assuming constant voltage model. So in the previous slide, we have assumed ideal diode model. So there is no voltage drop across the diode. But here I am assuming constant diode model, constant voltage model of the diode. In case of constant voltage model, what happens is we replace diode with a voltage source VD on when the diode is on, right? You remember in the constant voltage model, we replace diode or in other words, in IV, if I look at the IV characteristics of the diode when it is in the constant voltage mode, so this is my VD on. Okay, so VD on. So we are basically replacing diode with a voltage source VD on. Okay, and look at the polarity of this VD on. VD on will basically oppose the current, which is obvious, right? Because below the VD on there is no current. So now when the diode is on, if we measure the V out, we will get VD on, and when the diode is off, we will get V out equal to V in. Okay, so if I plot the transfer characteristics for this circuit, okay, we will see that when okay, so this is my VD on. When V in supply voltage is less than VD on, the diode is off, right? So diode is off means there is no current flowing in the circuit. So this entire voltage is across the diode. So we will get a slope of 1 up to VD on of the input. Now if we increase V in beyond this VD on, okay, then the diode is on. That means we can replace diode with a supply voltage VD on. So from this point, beyond this point, the output voltage will be equal to VD on. So if you look at the example in the previous slide, okay, here the example here in this one and the example here, the examples are same and the performance is similar. The only thing is this breakpoint moves to VD on. Okay, look at the graph. The breakpoint was in origin in this example, whereas here the breakpoint moved to VD on. Okay, because we are assuming the diode is replaced by VD on when it is on. Okay, now what about the example 4? Okay, again I am taking the same example which we have discussed in example 2. The only thing is here I am assuming we are replacing diode with VD on. Okay, so it is again self-explanatory that up to VD on of the input voltage the diode is off. Okay, so if we are V in is less than VD on, the diode is off. So entire output voltage, entire input voltage will be at the output. So here you see the slope is equal to 1, but beyond this point diode is on. Okay, so diode is on means the voltage across the voltage at the output will increase linearly with a slope R2 over R2 plus R1, because the voltage V in then will be dropped across R1 and R2 in a voltage divider mode, and we can easily find out voltage across R2 because voltage across R2 plus VD on will be your total voltage. Okay, and this will be the slope at the output. Now I hope these are pretty simple examples. If we discuss little bit complex thing, in here also I am assuming constant voltage model. Okay, so here when diode is off, so diode is off means, so we can say this V in will drop across R1 and R2, and we can find the voltage across R2. The slope will be this. Okay. Now when this V in is more than your VD on, okay, or the voltage here is more than that of VD on, okay, then your diode will be on. So we can say diode will on when V out equal to V in R2 plus R1 multiplied by R2. This voltage is voltage here across R2. When this is equal to VD on, then this diode will be on. Okay, so we can find out the input voltage at which diode will be on, so that the corresponding input voltage can be found out from this relation. V in will be equal to VD on multiplied by R2 plus R1 by R2. Okay, so this is I have written here, you see. Okay, so this beyond this point of input voltage, the diode is on. So if we now measure the voltage at the output, we will only get VD on, because diode is replaced by this VD on voltage. So here you see the voltage is basically, output voltage is basically VD on when the diode is on. I hope this example is clear to you. Again, we can similarly discuss example 6. Here, if V in is low, that will switch on this diode. Okay, and if V in is high, because this is connected to N terminal. Okay, whereas this point is connected to P terminal. So when it is low, then that will switch on the diode, and when it is high, that will switch off the diode. Okay, and when the diode is off, again V in is distributed, voltage is distributed between R2 and R1, and voltage across R1 is the output voltage. Okay, whereas when the V in is on, okay, when the V in is on, we will get a different voltage across the output. I think this is self-explanatory. Just try this, try to find this breakpoint back home and realize this plot. Okay, so let's move to in the same fashion we did. We found this breakpoint. Try to find the breakpoint here. Okay, now let's move and discuss graphical technique for circuit analysis. So far, whatever we have discussed is model based technique, which is much simpler, but because you see, nonlinear circuit analysis is not straightforward. Okay, so so that is why in case of diode we have come up with much simpler model and try to design and analyze those diode based circuits. Those circuits are pretty simple, but that will form the platform for more to explain more complex circuits. Okay, however, one can adopt a graphical technique, okay, to understand diode based circuit. One of this approach, as I said, is graphical analysis technique. In this technique, say this is a circuit example. This example we have seen in example 1 of the thing we have discussed. So so this is our example 1, you see. So this the same circuit we are looking here in the graphical analysis. In this case, we are taking into account two equations. One equation is this conventional diode equation, where this ID is proportional to exponential Vd over Vt. Of course, there is this -1 is there because of this reverse bias current. Now, so this is my this is the exponential relationship between ID over VD, ID and VD. We can plot load line for this circuit. So what is how this load line can be plotted? Okay, we can write V in this voltage is divided in two parts. One is the voltage drop across R1, and the other one is voltage drop across diode. Okay, so that is the output voltage basically, if we consider this as output. Anyway, so so this is our relationship between V in, ID and VD. Now we can have a straight line if you look carefully. So here in the x-axis ID is 0, on this axis ID is 0. So if we put ID 0 in this equation, okay, then V in will be equal to VD. Okay, so that is this point here. Here ID equal to 0, if we put V in will be equal to VD. Okay, what about when VD equal to 0? When VD is equal to 0, then we can say current ID is equal to V in over R1. So that is this point. Okay, so we can connect these 2 points and realize a straight line which is known as load line. So ultimately the solution of this circuit is where this exponential IV plot and this load line crosses or intersects each other. So in other words, as I said, plotting two simultaneous equations, diode IV and the above circuit equation, and locating their point of intersection will give us the solution. Okay, so so this is the diode current in the circuit, and this is the diode voltage in the circuit. So that is how we can have so this point of intersection will give you your between the load line and diode static curve, give you the solution. Okay, so this is another technique through which we can find the solution of a diode circuit. Let's just mention this point. If we use small signal, that is if we use a V in which is very small, okay, small signal analysis, then what will happen, this IV curve of the diode, the variation of this, because of this small signal, the current variation will be very low or very small. So if the variation, if we consider 2 points A and B, they are very close, then they can be connected with a straight line, okay, instead of these non-linear lines, right? So whatever I just now said, it is written here. If 2 points on the IV curve of a diode are close to one another, okay, are close enough, the trajectory connecting the first to the second point is like a straight line. Okay, and so we can find a slope of this straight line. Okay, so that will basically give you a resistance, that will basically give you a change in current because of that change in voltage, and that will basically give you a resistance. Okay, so we can write del ID over del VD, and we can write we can differentiate the current equation, and we'll have IS exponential ID1 over VT, and there is a VT term here. So this particular factor is basically your diode current. Okay, diode current. So diode current over VT is you see this is basically a inverse of a resistor, and this resistor is often known as diffusion resistor or diffusion resistance. Okay, so in case of small signal input, what we can do, we can replace diode with a small signal resistor, okay, which is known as diffusion resistor or diffusion resistance. This incremental resistance is known as diffusion resistance, or the inverse of that is often known as diffusion conductance. Okay, so you see here we have replaced diode with a diffusion resistance. So since there is a linear relationship between the small signal current and voltage of a diode, the diode can be viewed as a linear resistor. Okay, of course that we have to make sure that the change of that input signal is very small. Okay, apart from this diffusion resistance, there is also a capacitance associated with the diode junction that we will discuss in a minute. So whatever we have said so far, this is just written here. So this is your so if we change our voltage across diode, so this is the DC point. On top of that there is a small AC signal. Okay, so this is my small AC signal, and this small AC signal AC voltage gives rise to a variation in the diode current here. Okay, so you see this is my DC part of the diode current, and this is my AC part of the diode current, where this I naught over Vt is basically 1 over Rd. Okay, so if a sinusoidal voltage with a small amplitude is applied, the resulting current is also a small sinusoid around a DC value, which is obvious because here this DC point, or sometime we call it Q point, okay, the diode current will vary across this DC point because we have applied a small signal at the diode. Okay, small AC signal at the diode on top of that DC voltage V0. Now as I said, like we can also discuss the diode model for high frequency AC signal. Okay, for high frequency AC signal, so far whatever we have discussed, we have discussed the AC signal where the frequency of the AC signal is small. Okay, so we don't bother about the capacitance associated with diode. Okay, so capacitance effect is very small, so we haven't considered any capacitance in the diode model. But if the frequency of the AC signal is quite large, then we have to take into account a capacitance which is known as diffusion capacitance. Okay, and this is associated with a forward PN junction diode. Okay, if we try to so let me go through whatever I have written here. So no, let me. So I have a PN junction diode in the forward bias. On top of that, we have applied AC signal. That is, we have been discussing, right? In the previous case, we have mentioned that on top of this DC, we have applied AC signal. So same thing we have discussing. The only difference is now the frequency of the AC signal is quite large. Now what happens, because of this AC signal, you see this forward bias take the electron to the N side. Okay, so we will have electron concentration. Okay, we will have electron concentration So this is my electron diffuse in the p region, okay, and started recombining with the holes in the p region. Similarly, the so these are the electrons. Similarly, the holes from p region go to n region. They will also diffuse in the n region and started recombining and so on. So this is known to us. Now what happens is, say this is my electron electron which is concentration is decreasing in the p region. Okay, so this is my p region. This is when we have applied a diode voltage V0. Okay, on top of V0 we have a AC signal, say Vs. Now in the positive half of the AC signal, okay, more number of electrons will manage to cross the junction. Okay, whereas in the negative half of the AC signal, okay, less number of electron will manage to cross the junction. So you see, around this V0 equal to 0, for this variation in the because of this AC signal, extra amount of electron will enter to the p region, or lower amount of electron will enter to the p region. The same thing will occur in the n region as well. That is what I have tried to write here. Due to increase in input signal voltage delta V, this delta V is occurring because of this variation in Vs. Okay, that AC signal positive half cycle. When there is positive half cycle, the whole concentration crossing the junction, here I have talked about hole, although I have drawn electron, is the same thing. Okay, whole concentration crossing the junction will increase, which is obvious, compared to the DC voltage. Okay, so that is what I have said. In case of negative half cycle, the whole concentration will decrease. The similar change will happen in p region due to the change in electron concentration coming from inside. That is I have drawn here. So this diffusion capacitance, so because of this change in minority carrier, okay, so the diffusion capacitance is the change in stored minority carrier charge that is caused by the change in the voltage. So this voltage gives rise to change in the minority carrier concentration, and we will get a capacitance CD, which is known as diffusion capacitance. So the diode can be modeled this CD in parallel with this RD. Okay, of course you will not consider CD if the applied signal is of low frequency, right? So here with this I am closing this chapter. In the next class I will basically discuss diode applications. Okay, we will go through diode as a rectifier. Okay, where we will go through half wave, full wave and bridge rectifier. We will also discuss limiter circuit using diode and clamper circuit using diode. Okay, so see you in the next class.